Hi, my name is Chu Kok Yin. Now I'm going to talk about the design and implementation of platoon of miniature vehicles. Platooning system is a technology consisting of a group of trucks moving with small intravehicular distance. The leader truck is controlled by human and followed by the self-driving trucks. To perform V2V communication, networks such as 5G or Wi-Fi is required to exchange data among the trucks. This technology aims to improve the traffic congestion and reduce CO2 emission and avoid car accident, reduce the driver cost, as well as reduce the error caused by human. This is the software used in this project. Scala and OpenCV are the simulator. Whole project is using Python as the programming language. Ubuntu is the operation system. ROS, which called Robot Operation System, is an open source tool and software libraries helps to develop and build between robotics application. Wi-Fi is used to communicate between each hardware components. They are the hardware components of this system. At least two deep racers are used to perform a platoon. Driving wheel is used to remote control the leader deep racer, and all deep racers have been installed an USB camera and LiDAR sensor. This is the overview of the hardware connection. On the right hand side, the driving wheel with pedals is connected to the remote desktop by using the Wi-Fi so that I can control the leader by using the driving wheel, and all the racer can exchange the data collected from the LiDAR sensor with each other. The image from each USB camera can be also streamed to the remote desktop. This program could show subsystem remote driving. The control signal is published to the menu drive, which is the velocity gross topic on the deep racer. One important thing is that the driving angle have been enhanced by 10 times, so that the rotation angle required will be smaller on the driving wheel to rotate the deep racer. In order to limit the speed of the deep racer, I reduced the throttle output of the pedals. This subsystem is called teleport monitoring. Both images show the reel of USB camera on the deep racer. By using the ROS, the image topic have been published so that I can subscribe this topic to stream the video on the remote desktop. Another subsystem is the control system, which is the autonomous driving system. To simplify the program code, I have used a Python library to perform the PID to optimize the throttle and rotation angle value. As the minimum and maximum speed of the deep racer is from negative 0.7 to positive 0.7 respectively, thus the maximum upper bounding of the throttle will be set to 0.5, which is about 50 cm in order to avoid overspeeding and collapse with the leader deep racer. The maximum and minimum steering angle is from negative 1 to positive 1, and the value to be input to the PID controller is the calculated distance between leader and follower and the value of the orientation angle. Finally, we will get into the platooning system by using the data exchanging method. Please look at the figure on the top. There are two subscribers. One is subscribing the leader position data topic, and other one is subscribing the follower position topic. And please look at the figure at the left hand corner. There are two callback functions to callback the subscriber position data, including the XY coordinates and theta of the leader and follower. Those data will be used in the program code shown in the figure at the right hand side. By using the position of leader and follower, the distance between them can be calculated, and also the rotation angle can be obtained by subtracting the follower theta from the leader theta. After that, the speed and rotation angle will be optimized by the PID controller. Finally, the follower will move only if the distance between the self and the leader is larger than a certain value. In this example, the follower will move if the distance is larger than 0.4, which is about 40 cm. This is the experiment or the demonstration of the platooning system. The first experiment is to run the platoon system in a circle for several laps. Another experiment is to run the platoon system in a straight line. So after the experiment, I found that there are some limitations of my platooning system. The first one is the collapsion. Because the deep racer have no brake function, so that they need to stop by inertia. And during the experiment, I have tested to run the leader in a very high speed, and the follower will have no enough time to stop if the leader is stopped suddenly. And my solution is to drive the leader slowly to provide enough time for the follower to stop if the leader is stopped suddenly, and to avoid the collision with the leader. And another problem is the drifting of the LiDAR sensor. Because the LiDAR sensor drift during the rotation will lead to deviation or getting lost of the follower. During the experiment, I have tested the deep racer to drive in a circle. After several rotations, the follower moved in a larger rotation angle, which means the follower cannot turn properly after the leader is turning. As a result, the follower cannot complete the circle and maybe get lost after running in several laps. And my solution is to add an IMU sensor to estimate the relative position of the deep racer and combine the leader sensor and the IMU sensor measurement. And hopefully I can add this IMU sensor to improve my platoon technology in the future. That's all. Thank you for your attention.